All right, guys. So we have gathered here to do the quiz first. There are two quizzes that we are going to review, quiz 0 and quiz 1. I noticed that most of you have done quite well in the quiz. It's a reality check. It means that if you have done the quiz and you are scored highly, you have understood the material. As usual, every week I'll release quizzes. Those quizzes will get progressively more technical. At the moment, we have just entered deep learning, so the quiz pertains to the material we have done. As we move forward, you'll notice that the quizzes not only pertain to the material of the last week, as a review, they will also contain material from the weeks before that. And you have to be mentally prepared that it is a comprehensive quiz. And so you'll keep on getting review on all the material that has been covered in the earlier lectures and the earlier sessions. The quizzes will also cover the lab, as you may have noticed that this quiz that I gave, quiz 1, quite a bit of it pertained to the lab, and you would have done it if you have reviewed the lab. Fortunately, the performance in the quiz is quite good. So I'll keep the reviews rather short because it seems it's somewhat redundant. I'll explain through the solutions, and I'll pick up somebody's solution to explain through. We'll do the quizzes in the first half hour. After that, we'll take a lunch break. After the lunch break, about half an hour lunch break, after that, we'll start the Python session. Right? And after the Python session, I'll open up the flow to any one-on-one help you need, a clinic. Right? So you can individually stay back and say, I need some time, and can you please help me with this? We'll do it in a slightly open forum because quite often the problems that you are having are also the problems that others are having. And some people stay back just to see how those problems are solved. So let's do that. Okay. So with those words, I will actually switch over to a different screen, to the screen where we are talking about. So once again, to recapitulate, this is our course webpage. If one of you have not attended this, I would suggest you do that. There will be updates on this. Whenever I update it, I'll try to remember and put a note in Slack. If you have not joined Slack, it is high time you did it. Otherwise, you'll start falling behind. It is possible now that as Slack becomes a primary means of announcements, I may not get time to send emails. So
Asif, I've got a new computer, and so the Slack channel is what, supportvectors.com?
No, supportvectors-ailab.slack.com.
Okay.
Maybe that is a very good point. I should mention it perhaps somewhere, right in here. Why not add it? Let me just add it while we are at it before I forget. Add a resource URL. Slack. Slack.com. So this channel is a private channel. You won't be able to see when you just register. You have to send me an email to register.
Thank you, Asif.
So you haven't, Albert, registered, I guess.
I have registered. I have access to this page.
You do. Oh, nice.
I'm good. There I'm good.
Okay, good. So, all right, guys. So we will go now to the quizzes. Here is the quiz. I will just stop sharing for a moment because this is a privacy, individual people score. I will take, okay, I'll share again now. Where do we go?
As if you could increase the font size.
Yes, I will do that. Bear with me. Better? Is this legible now?
Yeah, thanks.
Yes, Asif. Yeah. Good.
So, guys, the questions were as follows. Consider a set alpha beta. Let us now look at a data set where there are n predictors, each of which is a numerical predictor. There is a target variable taken. There's a misspelling here. There's a target variable that takes value within the set G. Which of the following mappings represents a model that can predict a value in G based on the predictors? So guys, this was perhaps the question in which many of you stumbled. So I want to give you a tip. See, math is written in a slightly formal language, but the way to make it real always, before you solve a problem, make it real. So you notice that G is a set of alpha beta. Try to relate it to what we learned. We talked about cows and ducks. So alpha could be cow and beta could be duck, right? Then it talks about n predictors. Well, if you're trying to find out whether something is a cow or a duck, we can think of all sorts of numerical predictors, like measurable. Numericals are measurables, things that are amounts. So you can think of things like size, weight, and so forth. So those are numerical predictors. So now if you ask this question, if you bring it down to earth, this question becomes, there is a mapping from these values, height and weight, to either a cow or duck. It's a function. It's something that's trying to determine, based on the height and weight, whether something is a cow or duck. So is it a classifier or is it a regressor?
Classifier.
It's a classifier because what it is based on the target variable. The target here is categorical. And this notation, I wanted to introduce to quite a few textbooks you'll see will write it as this. If the target space is made up of this, something like this. And G is often used. Some people use C with a cut in it. I don't like that because the C with a cut in it, Blackboard C, is more reserved for complex variables. So G. So what are we mapping to? We are going from, let's say in the case of height and weight and size, r squared, right? Weight is numerical, size is size is numerical. So a real value would be r squared, and from there this function is mapping you into a cow or a duck. So this is the appropriate answer. And that is how you should reason with math. Math is always a generalization of some specific example. So the way to think about any of the mathematical things is to always think of a specific example that fits this generalization. And when you can think of a specific example that fits the generalization, it becomes a whole lot easier to reason about it. Okay? And this sort of a tip, it's a very basic tip. I learned it actually when I was doing my doctoral work. Many of you know that between my undergraduate in engineering and my graduate school in engineering, I took out 5 years to do a doctoral work in mathematical physics, theoretical high energy physics. So what used to happen is it was in the twilight zone between a lot of physics and a lot of mathematics. So you would go and read a book, and the book would start out very, very abstractly. And I would be just puzzling over what it meant. It took me a long time to figure out that one easy way you can always understand the mathematics is just try to take a real world situation, real world example, and see if it fits into that mathematics. And if it fits into the mathematics, now you have human intuition. You have intuition that you bring from your experience, and it makes understanding the mathematical notation much easier. So that advice, if you can remember, it will always help you. In machine learning is again a twilight zone between many fields. It is partly computer science, partly statistics, and partly mathematics. So one of the things that has been happening in this field is a lot of the things that I used to do in the early 90s and used to be called theoretical physics, they have made their way into this field of machine learning or artificial intelligence, especially artificial intelligence. We will talk a lot about energies, and we'll talk about Gibbs functions and Boltzmann machines and things like that. Pretty much the architecture and vocabulary of theoretical physics seems to have come in, you know, the Ising model and Markov chains and so forth. And all of those things deeply imbue this field. So because many people contribute to this field, you see a variety of languages, dialects in a sense within the field. The programmer will start out with code and will sort of stay pretty much close to code. And when you look at the mathematics, it's sort of very sparingly mentioned. Then you will have the theoretician will come, the statistician will come and talk all about tests, statistical tests and different statistical learning and so on and so forth. Is getting very mathsy enough. And then people who have deep theoretical background, they will come in and they will talk about quite a bit of, they will come in with a lot of mathematical notation. Now, why do they come in with mathematical notation? Are they just obnoxious people who are trying to intimidate you? It's not like that. For them, that mathematics is the most natural and most obvious way of explaining things. They write it like that because they say, this is the simplest way that one can explain something. Right? So it's just a dialect, it's just a cultural difference. But once you get used to the mathematical notation, and in this course, if you notice the textbook that I have prescribed, it does not spare the mathematical notation, it does use the mathematical notation. And the reason for that is, on Mondays, I want to make sure you become good, you get a very good theoretical foundation. On Wednesdays, you get a very good programming and practical foundation. So you're strong on both the legs. So we are going to use that textbook with notation. But this notation, once you get familiar with it, you will agree that actually it says things much more clearly than is said with long paragraphs of English text. Right? So we will get used to the notation. Anyway, this is that. This thing is nothing but this. And then obviously, these are different permutations to confuse you in case you were guessing. Now, which of these are classification tasks? Let us go one by one. Given geospatial data on housing, discover the neighborhood clusters of houses. When you look for clusters in data, you're not predicting anything at all. It is pattern recognition. You know, you fly on a balloon over San Francisco, and you notice that all the financial district is clustered together in the tip of the peninsula. And you happen to notice that then there's a whole cluster of trees, that is the San Francisco or the Golden Gate Park, right, in the city. And then you see a cluster of residential houses a little bit down the peninsula. You recognize a pattern to the layout of the city. And that pattern recognition is not classification. Classification is all about predicting whether something is this or that. So obviously the first one doesn't fall into that category. What about the second one? Given the credit history of a person, predict whether or not the person will default on a loan. So what is the target variable? Who would like to articulate what the target variable is? What the G is?
Default or not?
To default or not, right? So this is a crucial question. When you apply for a mortgage, the only question in the bank's mind is, will you default on the loan or not? Right? So that is a classification task. Next, given some historical weather data for Fremont, predict the noontime temperature tomorrow in the city. So what is the input data? It's the weather data for Fremont. If you had to predict the temperature at noon tomorrow, what do you think that is? What is the target variable here?
Numerical.
It is?
Numerical word.
So a little bit louder, please.
It's a numerical value, sir.
It is a numerical variable. Excellent. And so this is a problem in what kind of a machine learning algorithm is it?
Regression.
Regression. Excellent. So this is a regression problem and not a classification problem. Given the credit history of a person, predict the credit score for the person. So when you get your credit score from one of these rating agencies, is that an identification or is it a quantity? It's an amount, it's a number.
It's a number.
It's a number. So it's not a classification problem for the same reason. Now the last one, given the polling data, predict which of the two leading US presidential candidates will win the upcoming election.
Classifier, yes or no?
Yes, you have to pick one or the other, and that is classification. It is the classification problem that all the pollsters are busy with today, making predictions.
Mm-hmm.
So deep learning refers to data scientists learning data science deeply. I believe all of you got this right. Now, deep learning is a buzzword that is often associated with the application of deep neural networks to problems. Right? It's one particular algorithm, family of algorithms within machine learning. Question 4, consider a data set where there are n predictors, each of which is a numerical predictor. There is a target variable which is also numerical, real valued. Which of these is the correct mapping from the input feature space to the output feature space? So guys, if there are n predictors, each of them real valued, the space would be a Cartesian R to the n space, isn't it? So think of it as two variables. Let's say height and weight of a person, and you're predicting the person's age. Now we have made it a little bit more real, right? Map it to a real world problem. You're looking at a person's height, you're looking at the person's weight, and you are trying to predict what is the age of that person that looks like it. Now you can imagine that the input space is a Cartesian space, right? X-axis could be height, the Y-axis could be weight, and you're looking at a simple Cartesian coordinate space. And the target space is just a line. You know, what is the age? Age goes from 0 to whatever, maybe 100 or whatever, right? 150, the human age. So you're going from input to an output. The input space is, now we generalize from there. If there are not two predictors, but n predictors, the input space is R to the n, and the output space is just R, it's just number. When you have just R, there is a word that we use in machine learning and AI. People use the word scalar. It is a word that is often sort of mispronounced. Where is my scale here? Okay, so imagine that you're holding a scale in your hand. What does a scale do? A scale helps you measure something, right? How big is it? How tall is it? Or something like that. So from that comes the word scalar with a A at the end, S-C-A-L-A-R, scalar. Mathematicians often use the word scalar for a measurable quantity, something that can be measured with just one number. If you can measure something with just one number, it is a scalar. So what is an example of not a scalar? The example of not a scalar could be given a car on the highway, what is its coordinates? Well, now to give the coordinates, you need two variables. You need the latitude and the longitude, isn't it? Now, to describe the car fully, you might even say, I don't just need the latitude, longitude, I also need the velocity. Right? And so you can say velocity will have components, velocity along the latitude, velocity along the longitude. And you can go even further. You can say, what is the acceleration along the latitude direction and the longitude direction? So now you have 6 variables describing the car's coordinates or behavior. Or, so then you have a 6-dimensional space. And so you generalize from there. Here we have Rn to R because the target variable is a number. Now in regression, what is the target space? Is it 1-dimensional, 2-dimensional, 3-dimensional? What is it?
1-dimensional.
Say that again.
I think it's one-dimensional.
Yes, fine, you're right. In regression, the target space is always one dimension. Now, sometimes people do multi-regressions in which they will predict 2 or 3 things at the same time. Those are sort of the exceptions. Usually, your target space is simply one dimensional, and that is something to remember. Input space can be complicated. You can go from any dimensional space, but the target space is always one dimensional. Again, for those of you who have done ML100, 200, this should be hopefully very easy. Now, which of these are examples of supervised learning? Given some geospatial data on housing, discover the neighborhood of clusters, neighborhood clusters of houses. That is, again, as we talk, pattern recognition. That is not supervised learning. What is supervised learning? Supervised learning is a learning in which a machine learns to look at input data and predict value in a target space. Right? So it is usually classification or regression. If it is not classification or regression, it is not supervised learning. This is again a review of the vocabulary. And this word reminds me of something. Sometimes I have conversations with businessmen and they ask me, so how are you doing this? I says, we do this. And they ask, is it supervised learning or not? And I say, yes, it is supervised learning. So they said, no, actually we want more advanced AI that can solve this problem without supervision. In the AI learns on its own. Right? So that is a misunderstanding, of course, from the businessmen. They have no clue about the word supervised and unsupervised words. What do they mean within the AI field? We have a special meaning for it, and it has nothing to do with whether or not you're hanging around supervising the learning process while the machine is trying to learn. So given the credit history of a person, where it should be a person, predict the credit score for the person. We are predicting a score, a number. It certainly is a supervised learning. The second also is supervised. So the rest of it is simple. You just have to look at the target variable. Is there a target variable or not? If it is, then it is supervised learning. If it is not, you just discovered the clusters. You didn't predict anything, which is true in the first case, then it is not supervised learning. Next question. Imagine that you have built an AI model that can distinguish between a cow and a duck. The inputs to your model are the weight of the animal and the size, volume. Whether the animal, and the third predictor is whether the animal has a beak and whether or not the animal has wings. Which of the following statements are true? Now, the first is the AI model is a classifier because the output of the model is an identification of the animal as a cow or duck. I hope by now we all agree that the target space is cow or duck, and therefore it's a categorical problem. The second statement, the AI model is a regressor because regressors have the output as categorical variables. That, of course, would be folly. The AI model is a clusterer because cows and ducks tend to roam around in clusters. Again, no. AI model is a regressor because two of the features, weight and size, are numerical, real valued. And this is something to remember. Whether it's a classifier or a regressor depends completely on the target space. It has nothing to do with the input space. Input space always will become, one way or the other, a Cartesian space, R to the n. Even if you have categoricals in the input space, like whether or not the cow has duck, whether the animal has a beak or not, has feathers or not, you will treat it as a zero, you'll treat it as a Boolean, and ultimately you'll have to treat it as a Cartesian space. Okay? So, well, we'll deal with that later. So the only thing that makes sense here is the first one. This was a one that some of you got wrong, actually.
Asif, a little theoretical question there.
Yes.
If you're faced with a problem where in your input, they're all categorical variables, would you ever be able to predict a continuous variable in the output?
Yes, yes, you very well can, actually.
Okay.
So I'll give you an example. Suppose your input is one of the 10 species of animals, right? And your output is the median lifetime of that animal.
Okay. Yeah.
Next question. Imagine a young entrepreneur who opens an ice cream shop on the beach of her hometown. Now she needs to estimate how much ice cream will sell on a given day. So she can purchase an appropriate amount from the wholesaler. If she purchases too much, it will go to waste. If she purchases too little, she will lose the business. So it is important that she builds a model that can predict the amount of ice cream sale on a given day. She observes that the contributory factors for the amount of ice cream sold on a given day on the beach are temperature, day temperature on the beach, whether or not it is a weekend or holiday, wind speed, whether it is sunny, overcast, or raining, whether or not the competing ice cream shop is open. Which of the following statements are true? Her model is a regressor because the prediction is the amount of ice cream sold, likely to be sold. That is true because what is the target variable? Amount. The moment you see the word amount, it should give you a clear indication or a clear hint that you are most likely looking at a regressor. The target space is an amount, right? So in other words, it's a scalar, it's a measurable. The rest of the answers are not true. Her model is both a classifier. Other than that, see, once you get this thing clear in your mind, that it is the target space that determines whether you're doing classification or regression, then you won't get it wrong. And so this question was sort of a review for most of you, I hope. Imagine that you have built a model that underfits the data. Likely because your model is simpler than the underlying ground truth. Which of the following is true about the errors in the prediction? Now, those people who are entering the field of AI for the first time, you wouldn't be expected to get this one right. This has to do with some prior background in machine learning. We will cover this material in the coming lectures, so don't despair. We will review this. So what happens is when models have, there is a ground truth. When you get data, the problem with machine learning, or the central core problem with machine learning, is you don't know how the data got created. So you make all sorts of hypotheses about what is the relationship, what is the function that maps from the input space to the output space. It is some function that is unknown, but you know that behind the data is some generative force, some causation, and that causation is some mapping, some function of the inputs to the output. But that function remains hidden from you. You cannot find that. So what do? The point with machine, can you discover that function? Well, there's a famous statement by Box, and Box was a great scientist in this field. He said something very interesting. He said that all, and I would paraphrase it and say machine learning models, all models are wrong. All models are wrong, but some are useful. So what did he mean? How can wrong models be useful? Would anyone like to elaborate or take a guess on that? How can you say that something is wrong and it is still useful?
It's more near to reality. Means it's not accurate, but we can get like 90% or 80% times right.
Yes, it's an approximation of the reality. That's the main point. So it approximates whatever the ground truth was, which you can never know, but it approximates the ground truth with reasonable fidelity. Are we getting that? Right. So maybe I should illustrate this because this bias variance, some of you don't know, I'll illustrate this by making a drawing here. So let me know when you guys see my writing screen. Are you guys seeing my writing screen here?
Yes.
Okay, let me, oh, sorry, what just happened? I think I just closed it. 1 second. Huh? going to maximize it and do this. All right, much better now. So suppose the ground truth is like this. You have data, and the data comes, this is your x-axis, and this is your y. The y is the target variable, target and predictor. And you can, like I said, it's always helpful to give some physical meaning to it. So let's say that based on height, this is the height, you're trying to determine the age of a student. Right? You're in a school, you look at the height, and it's somewhat of a predictor of age. Right? Now, what may happen is that the relationship may be, and obviously I'm not a medical or a biologist, so I'm quite likely going to draw something that in de facto reality may be completely wrong, so forgive me for that. But let us say that the relationship is like this, that children are born, all of them, at when y is 0, you nonetheless have a certain height, and your height asymptotically goes like this. And then it plateaus off at some age. Right? We don't grow anymore. So let us say that this is the relationship of height to age. Now, what you can do, let's see what are the sort of models you can build. You can build a model which is like this. Let me call it model 1. And one way to think of model is models are hypotheses. This is your first hypothesis. It could be something like this. It could be something like, let me take another hypothesis. It could be something like this. Oh, no, actually, let me take this out. Draw it better, a quadratic hypothesis. It's not quadratic, third degree hypothesis. So let us say that your hypothesis is something like this. Right. Let me call it hypothesis 3, and it bends back up and so forth. And that's your next hypothesis. And then fortunately, somebody comes up with a hypothesis which is like this. Another hypothesis is like this. So let me call this hypothesis 3. 2. Anyway, this should have been 2. Hypothesis 2. This is hypothesis 3. So do you notice, guys, that each of these makes some mistakes? Right? Some places it gets right, some places it gets wrong. Right? And depending upon what you're trying to do. So suppose the only thing we are looking at is children, and children are up to high school. So your data range that you really care about is only up to here. Let's say, no, I can't. This, no, it's not showing through. All right, I'll just use this box. Huge. Suppose you're only concerned with ages 0 till this age, school children. Right? You don't care about making predictions beyond this box. So when you look at this data, clearly you can see that all of these answers are partly wrong, isn't it? None of them could come up with the yellow line. Right? And the yellow line is sort of more like a log curve, but it didn't. None of these could come up with it. But you also see that each of them got it partially right. Each of these hypotheses got it somewhat right. And that is what is meant by Bock's famous statement that all models are wrong. The ground truth, you'll never know. You start with data. When you start with data, no angel is coming and whispering the ground truth to you. Because if an angel came and whispered to you the ground truth function, there is no need for machine learning. But what we do is we try to create functions. We try to come upon functions. So suppose let ground truth be y is equal to some g of x. What you do is you come up with y hat is equal to some f of x, where you hope that fx is approximately g of x, at least in the domain of applicability, at least in the domain of applicability. Now, what in the world do I mean by this fancy statement, domain of applicability? I just used a bit of a mathematical jargon, but looking at this problem, can you trace it back to the example or the reality and tell me what is my domain of applicability here?
School age.
School age, yes. This from here to here is my domain of applicability. Within this region, I want a model that works. And you can see that different hypotheses, they work to different degrees, isn't it? Now comes the interesting thought. They all are making mistakes. They all are making errors. And the errors that remain, even when you fit the best possible line, the best possible quadratic curve, a parabola, or the best possible, let's say, a third degree thing, something like a sine wave, 3 bends to the data, there will always be errors. By the way, I talked about the bends. It is one fact that I sort of mentioned in the previous workshop, but I'll just mention. Here is an intuition in machine learning that a lot of people actually don't have. See, when you see data, suppose you see data like this. Ask yourself, how many bends do you see? In this data, how many bends do you have?
0.
0, because this can be approximated like this. Now, if you take another curve, something like this, data always comes with noise. Why does it come with noise? The process of, see, you notice that data never is clean. It always has noise in it, right? All the points don't fall in space. So we will address that question in a moment. This kind of a curve, if you approximate, it is this. How many bends does it have? One bend, right? You have bent a straight line once here. So bend is equal to 1. Right. And now I'll tell you something which is actually very elementary and extremely useful when you are doing data analysis with people. It turns out for some reason are not aware of it. So suppose I take a curve like this. Sorry. Let me put some noise here. How many bends do you see? Here and here.
2.
These are the 2 bends, right? And here the bend is at this point 2 bends. And so I can keep moving forward. Like I can have a situation with 3 bends and 4 bends and so on and so forth. Now it is a very interesting thing that if you write it as a polynomial equation, right? Whenever you have this and you try to do polynomial approximation, again, that's a hypothesis, right? You're trying to say, I see this data with noise, and I'm going to approximate it with a polynomial. Here's the intuition you can use. A straight line is beta naught plus beta 1x. So what is the highest degree of the polynomial? It's a polynomial in degree. A line is a polynomial of degree?
1.
Right. It's of degree equal to 1. What about this? This can be written, you can convince yourself from your high school algebra that you used to write it as, you wouldn't use beta, you would use ABC x square. Are we together? And here, so degree is
2.
2. And the only task you're left with is finding the values of beta naught, beta 1, beta 2, the best fit values. And that's a problem of machine learning. And here it would be y is equal to beta naught plus beta 1x plus beta 2x squared plus a beta 3x cubed. So degree is equal to 3. So what do we learn from that? You look at the data. So from that we learn, let's give an intuition here. Learn that to approximate a data where we observe let us say k bends, we need a polynomial of degree. How much? Degree. So for 0 bends, you needed 1. For 1 bend, you needed 2 degrees. For 2 degrees, you needed a 3-degree polynomial. So if you have k bends you observe in the data when you eyeball it, what is the polynomial that you should write?
K plus 1.
K plus 1. K plus 1. So in other words, your equation should be y is equal to beta naught plus beta 1x plus a beta 2x squared plus a beta n xn, right? This has to be your equation, right? And then if you want to, okay, so we have this bend. Now it raises an interesting question. The question that it raises is that if I can approximate data. So just think in terms of one dimension. One dimension makes machine learning very easy to understand in some way. And then we take our intuition to higher dimensions. Right? Then you can take it to 2 dimensions. So a curve in 1 dimension becomes a surface in 2 dimension. And then in 3 dimension, if you have, what is a 3-dimensional surface? It's sort of a hypersurface. It will exist in 4 dimensions and so forth. So the best intuition, of course, is we all like to think in terms of 1 dimension. Life is easy. Up to 2 dimensions, like when your surface or your hypothesis curve surface is 2-dimensional, we can visualize it. Beyond that, you just in your mind generalize it. So I have a joke in my field, which used to be theoretical physics. There used to be theories like there are still superstring theories and so forth, and they talk of 10 plus 1 dimensions. So one of the questions that comes is, how do people think in terms of 10 plus 1 dimension? So I'll tell you my little trick. Right? Whenever I would think of a problem, I would think in terms of 2 and 3 dimensions. 3-dimensional space, 2-dimensional surfaces. And then you develop your intuition, you solve your problem with that, like the way we are doing with cows and ducks. But then when you speak aloud, you say, as you can see in arbitrary dimensional space, this hypersurface. You see how it is? Because you're confident you can generalize, you write as though it is in a generalized higher dimensional space, but you develop your intuition always in low dimension space. Anyway, that's sort of a joke. So now why did I bring that here? Let's go back to our situation. Suppose your data is like this, and I'll give you an approximation. Suppose the data is like, how should I put it? This. I'll deliberately take a 2-dimensional surface. This is again a review. Those of you who have been with me in the past would remember these arguments. So you would imagine that the ground truth should be this. This is your ground truth. Truth that you don't know. Right? That you don't know. And suppose, see, when you are dealing with data in 1 dimension, the best thing you can do is just go and visualize it. It will give you a hint on what to do. Even with 2 dimensions, you can visualize and see what is going on. Right? I mean, this is 2-dimensional data and you're searching for a 1-dimensional curve. Or 3-dimensional data and you're looking for a 2-dimensional surface. It helps to just visualize and get a clue. But let us say that you can't. this data is actually very high dimensional and complex, and you can't do this. And this is how the data scatters in this space. Right? So then you can build, once again, multiple hypotheses. Let's do that. You can have a hypothesis that is that it's a straight line. So you could do, if you try to fit a straight line to the data, actually you won't do very well. The best fit straight line would be something like this, right? This is the line hypothesis. Oh goodness, this is a multicolored pencil I seem to have picked up. Okay, this is the line hypothesis. Why? Because for half the time, this curve seems to be going up, for the other half it's going down. If you were to actually do a linear regression model, you can verify that this horizontal line is what it will come to. If you do a quadratic equation model, then a quadratic equation model would actually fit the data like this. This is your quadratic model. And suppose you did a third degree model. So let me take another colored ink here. Suppose you did a third degree model. What you might end up with is something peculiar, actually. It needs one bend here, but let me do, maybe it will end up with something like this. This is a third degree model. And if you make, let me take a model that is really high dimensional. Suppose you took something like a 5th or 10th degree model, you'll end up with model like this. I'm just sort of conveying the concept here. So of all of these models, if you start with the first dimensional, the hypothesis model, what would you say? You would say that it is very inflexible. It doesn't have any bends in it, isn't it? Inflexible, oversimplified model of data. What does this model say? That the output doesn't depend on the input at all, something like that. It's a linear model in this particular case, a linear model. You would agree that it is simpler than the ground truth. When you have a model that is simpler than the ground truth, the errors that you have are high bias errors. Are we together? You said that the model is biased. Now, without going into the definition of bias and variance, the physical intuition is if your hypothesis is simpler than the ground truth, you're suffering from high bias errors. On the other hand, when you look at the 10th degree polynomial and you are building an overtly complex model, your hypothesis is overtly complex, the ground truth is actually simpler than that. So what you have is a model that sort of shows high variance, right? It shows a different kind of errors. It has high variance, right? So I'll mention this as a fact, and I'll post these notes. Overtly simple models will have high bias errors. And overly complicated, it's not overly, excessively, let me just use the word excessively, that would be better. Excessively simple models and excessively complex models will exhibit high variance errors. And these are also called overfitting errors. High variance errors, and this is underfitting. And these words, obviously, those of you who come from a prior background with me know, but at this moment, I'm just giving a taste of it, and of these words, underfitting errors. Are we together, guys? Huh? So that is the way to
have a question.
Yes, go ahead.
What happens if it's a circle?
A quadratic curve can describe a circle, There is only one uniform bend. It just keeps bending over and never stops.
Is it only one bend?
Yeah, it's only one bend. Think about it. You take a line and you bend it, but you don't just stop bending. You continue the same amount of bend all over. You'll come back to yourself. Right. So a quadratic curve will do it because one bend means quadratic. And as you know, a circle is described by a quadratic equation.
Yes.
That's it. So the bend doesn't change. It doesn't become straightened out and then become something else.
Okay. Thank you. Thank you.
Yeah, that's one way to look at it. But good that you asked that question. So guys, do we get the intuition? So when you make overtly complicated model, it oscillates. You have a lot of oscillations and you have overfitting problems, you have high variance problems. When you make overtly simple model, a hypothesis, compared to the ground truth, which remains unknown, you are making simpler hypothesis, and that too simple a hypothesis, and that gets you into trouble. Now, with that a preliminary there, what happens is, suppose you take the degree of the polynomial, the complexity here, degree of the polynomial is a good proxy for it. Let's say K, degree of the polynomial is going like this. What happens is that there are two kinds of errors. The bias error, let's say, the bias error will keep going down. So this is the bias error. Bias errors. And the variance errors is, it tends to go up in the beginning, very low variance, and then it tends to go up like this. So this is variance. And this is a famous curve that you find mentioned everywhere, bias variance. So that the total error that you see in the model is the compromise between these two. It's somewhere like this. If you add up a bias plus variance, the total error, E total variance. Actually, it isn't just bias plus variance. There is also a part which you can't help, which is the epsilon. Does anybody remember what we used to call this? What is the other mysterious thing there in the equation?
Irreducible errors.
Excellent. It is the irreducible error. Where does the irreducible error come from?
The factors that are not included in the model, like the features, like.
But that is right. It has two principal causes. I mean, many causes, but roughly speaking, you can put them under two buckets. But they are either instrumentation error. No instrument is perfect, right? So if you measure the temperature, you get different thermometers if you are really measuring, being very precise, it will give you different values. If you take a very sensitive thermometer and one of those laser thermometers, you try to measure temperature of something, it may literally give you different values from second to second, right? And so there are instrumentation errors. Then along with the instrumentation error, I'll also include the human error, some typing errors people make or people do all sorts of things. Then the other error is more genuine. It comes from that which you don't know. So when you say that the amount of ice cream sold on the beach, you try to parameterize it with or model it with the temperature on the beach, the wind speed. Let's say you take only these two things. Then there are factors that affect it, but they're there. You didn't take, for example, day of the week, whether it's a weekend or a weekday, holiday or not. Right? So what will happen is if you're building a model just with temperature and wind speed, for a given temperature and wind speed, all of these two being constant, you would still see a variation of values, Y values, amount of ice cream sold values. And that will represent whether it's a holiday or not, or weekend or not. It may represent whether or not it is going to rain, right? And other factors. Right? There are many factors that may play in. So you always have the irreducible error that sort of gives you a clue that there are things you don't know about the model. So the bigger the irreducible error, the more you should acknowledge that your model is the best you can do, but there is a lot you don't know. right? Irreducible errors, yes, so that's one way to look at the irreducible errors. Are we together? Once you have taken care of the bias variance trade-off, in other words, you try to build a hypothesis that is pretty much at the level or close to the ground truth. Then you have the least error, except the irreducible error stays. So with that of a background, I will come back now to our notes. It's a pretty long preamble. One question to ask is, well, let's take one-dimensional case. Isn't polynomial regression enough? If we can describe every data distribution with a polynomial, then why do we need the rest of machine learning? It's a puzzle. Who would like to answer that?
For very high dimensions, for very
forget high dimension. See, you can generalize from single to high dimension. The same argument applies. So stay with one dimension and say that suppose all data was one dimensional, like one target variable and one input variable. Yet, why is it that we need other algorithms at all? We can just start with polynomial regression and be done with it.
No, but classification, clustering, those cannot be that.
Well, let's only talk about regression. Let's keep classification and clustering aside.
Probably less explainable.
so when the data is discrete like 0, 1, 1.5,
okay,
not connected.
The problem and remove the non-complex, the irrelevant complexities. Really.
There are NP problems, right?
The quantity is a real number and the output is a real number.
No, there could be non-polynomial problems.
Excellent, Jay. Could you elaborate on it a little bit more?
You cannot represent by a polynomial equations. There are issues.
Excellent. And what are those distributions called?
Transcendental functions.
Transcendental functions. So, guys, there's a very interesting history to this. Regression, to the best of our knowledge, it started with a mathematician called Carl Friedrich Gauss, who was a child prodigy. He was the son of a very poor miner. And his father believed that life is hard and you should spend your time working in the coal mines. This boy was obviously built of a different fiber. He used to like numbers and things like that. And then he was fortunately a teacher who really liked him, went to universities and said, there is a child you need to take over, and he came. So anyway, that was Carl Friedrich Gauss. And there's a very interesting history to how regression came about. I'll just sort of tell you in a minute. What happened is that there was some planetoid or something in Europe that was supposed to come into the sky that was behind the sun, and it would show up in the sky after some years. What you had to tell is where in the sky to look for it and when, which day, what time should you look for it? When will it appear? So science used to be patronized in Europe through these competitions, just as we have Kegel competitions. So a lot of people put in their submissions of where and when the planet, I believe it's a planetoid that would show up. Then Gauss also made his submission. And when Gauss made his submission was practically on the dot. And everybody else was wildly off, completely wildly off, and all the other great mathematicians were off. So then, obviously, Gauss actually wrote a paper about it in 1793. When he did that, Gauss used to be a guy who used to hide some of his best tricks. So this principle of least square, which is the foundation of regression, the mathematics of regression, he was rather coy about it. He didn't reveal it quite clearly. He sort of alluded to something and so forth. Then in 1805, a mathematician named Legendre, he literally wrote the landmark paper whose title was least square, a method of least squares to solve problems. When you solve the problem using method of least squares, you're essentially doing a regression, or in the language of machine learning, you say it's the loss function. So when Legendre came out with it, then came Gauss, and he says, no, wait a minute, I discovered this first, right? And Legendre said, well, I didn't read your notes. I read it independently and I did it. So that battle raged for many, many years. Very recently, a great sociologist of science and statistician, Stigler, he resolved the debate ultimately by finding that the method of least squares was discovered actually independently by three people. Gauss was probably the first. Then came Legendre, and after Legendre, and independent of him, was yet another mathematician in US who discovered it. So anyway, that was that. When the method of least square was discovered, linear regression, what you would today call linear regression, then people generalized it to polynomial regression. That seems amazing. You remember, those were the days without computers. So all of these computations had to be done by hand. Imagine, right? You would gather people, mathematicians would sit and tediously do iteration after iteration to solve the problem 200 years ago to 300 years ago. So then, 300 years ago, so then they were doing polynomial regression with quite a bit of success, except that they realized that polynomial regression does not solve a large number of problems. It solves some, but not a large number of problems. And the reason for that is that there are inherently functions that are called transcendental functions, whose very definition is that if you try to write them as a polynomial expansion, and there's a word you may hear, that any function can be written in polynomial basis, it's called the Taylor expansion. If you do that, a Taylor expansion comes from calculus. Some of you may vaguely remember it. If you don't, it doesn't matter. But just take it that any function can be expanded into a polynomial equation. But when you try to do it with these so-called transcendental functions, the most easy example of a transcendental function is a sine wave, sine or a cosine, right? Think of sine wave. Then what happens is your polynomial will end up with infinitely many terms. So it will take an infinite degree polynomial to represent your function. Now I told you that infinite degree polynomial means there's a lot of bends in it, right? And in the sine wave, of course, you have a lot of bends. Now in many functions, you can't quite see the bend, that the bend or the slope is changing, but it is changing all the time, right? So the bends are moving around basically in the slope. So it turns out that those transcendental functions are everywhere: the bell curve, the sine wave, right? And so forth. In fact, nature seems to be treating, just as we use the English alphabet as a basic building block for words and sentences. One of the most remarkable things about nature is, for nature is written in the alphabet of transcendental functions. It's just amazing. You know, you look at an atom, the orbital structure are actually the harmonics, the modes of spherical Bessel functions, right? You beat a drum, those are Legendre polynomials. You throw a stone in the river or in the pond, the ripples will form a sine wave-like behavior, but the amplitudes will decay like Legendre's and so forth. So all around you, you know, people's heights, if you put together, they will show a bell curve distribution. Many things show a log normal distribution. So there are all of these distributions that are everywhere. And one of the things that I tell people in almost every workshop I do is that if you can make friends with transcendental functions. Take every month, pick one transcendental function and become familiar with it and see where you use it. These things are just magical beasts. For example, one transcendental function, some of them are, one of them is called Weibull. Weibull is the foundation of reliability engineering, Weibull and Gompertz and now so forth. But one function, Weibull, that was discovered by literally a guy named Weibull, many years ago, he submitted it to the Royal Mathematical Society saying, I humbly submit this function, which I hope is of some use. It turns out that much of reliability engineering uses Weibull functions. The reason that you can travel today from here to Europe or India or China or Korea or anywhere, and most of your worry is about whether you'll get a middle seat or a good comfortable aisle and window seat. You don't worry about the airplane falling from the sky. And yet an airplane contains millions of parts. it still reliably reaches the other end year after year. In fact, it is the most reliable mode of transportation. It is all because things are steady. There's a lot of reliability engineering that goes there. And behind a lot of that mathematics, behind quantum physics, behind all of nature are transcendental functions. So you would expect that when you look at data, you should suspect that transcendental functions are there somewhere in the background. One of the things you can do as a data scientist is you can often walk into a situation. If you know your transcendentals, you can spot it. And when you spot it, you can say, why not approximate? Why not model it using these transcendental functions? Now, when you walk into a crowd where people have just picked up from a programming book, machine learning and AI from a programming book doing, R and Python and I don't know, something, you will literally see them think of you as a magician because they have been struggling with the problem for quite some time. You walk in, and in the blink of an eye, you make a hypothesis, and that solves the problem. When it happens in those situations, when it does happen, those are really moments to cherish. You just feel great, and because you can walk in and solve a problem. So know your transcendentals. So that is one thing I would say. Now, what I would like to do is finish this particular quiz. Give me 1 second. Okay. Now,
so Asif,
yes.
I had a it's a very interesting discussion what we had. I had a very different question along the lines of the codes that you just mentioned, that any of the models is probably pretty close to the ground truth, may not be accurate. That takes me to the question. Actually, I had this in mind. I hold it for a long time. Would if we have AI now and we don't know any of the physical laws, would it be able to derive all the physical laws, all the theoretical physicists who are sitting and getting the equation using their without much data, like Einstein? Would we be able to?
Is a very good question you asked. What you're basically saying that just given data, the old way used to be scientists would study data, build hypotheses, they would write equations. And then from those equations, those became the effective models to make predictions. So if you really think of the law of gravitation, for example, what is it? It is an effective model based on the data. Kepler's law. Kepler was, I would often think of him as the original data scientist. He inherited the data from his great teacher, Tycho Brahe, the astronomer. This was the day before, so this answers to your question. Tycho Brahe was an astronomer before telescopes came about. He would look at the sky with just sextants and so forth. And actually, now we don't talk about that, but the bit of a history is that Kepler, he had an amazing life, but actually at night he used to be a bit lazy. So, and stars come out at night, especially at winter nights. Winter nights in Europe are cold. And Kepler used to drag his feet as a student as an apprentice with Tycho Brahe. Tycho would always tell him, you need to be a little bit more willing to go out at night in winter. So anyway, Kepler helped Tycho Brahe and inherited all his data. Today, then he studied that data and he studied and built models. He was your original data scientist. And he came up with the so-called Kepler's laws of motion, which he said that sun is at the center. It is at one of the focal points of an ellipsoid. And all orbits of planets are elliptical orbits, right? And ellipses have, of course, two focal points. Sun is at one of the focal points, and the area that when you connect the planet and to the sun, the line, the area that line sweeps per unit time remains invariant. Right? Those are the two Kepler's laws of motion. And how did he come up with? By studying data. He wrote down this equation. How would we do it today? If you make a black box model, like a DPI model, will it be able to predict that? Yes, it will be able to predict that. And this is the problem we are facing today. Has it advanced science at all? Has it advanced your understanding or given you a clue on the causative forces? It has not done that. You need to ask that AI to explain itself. Right? And then you may have some understanding of what is really going on. Right? And
the physical explanation is lacking. Okay.
Explanation is lacking. And this is an important point because in the hubris and excitement these days around AI, people are actually jumping around, especially in Silicon Valley, making bizarre statements that science, the old science is over. The only science that matters now is AI. Right? I don't think that is true. Just be warned that AI can do a lot of things. It is a tool to assist you in science, but it does not replace science. Right? Because science is about understanding the causations. Where is understanding in all this? But it's a tool. It's a very valuable tool.
Thanks.
All right, guys. So this is it. Now we'll quickly run through it because I know lunch is waiting for all of you. It's close to 1 o'clock. So we'll take the second quiz after the lunch, guys. Imagine you have built a model that underfits the data, likely because your model is simpler than the underlying ground truth. Which of the following is true about the errors in the prediction? So the models will exhibit high bias errors, right, as we just discussed. Question number 9, imagine you have built a model that has significantly overfit the data. Which of these would you likely see high variance errors? Which of these are regression tasks? This is very easy. I'll just leave it to you guys. I think most of you got it right. If it has to do with numerical target variable, it's a regression task. And that, folks, ends our first quiz. Let's take a lunch break. Let's regroup at 2. We'll start with the second quiz, and then we'll go to the Python, those of you who are interested in learning Python.
Same link?
I will end with one statement, guys. See, the world has heard of Kepler, right? But Kepler stood on his data came from his teacher and his master, Tycho Brahe. Right, Kepler was a predecessor of Tycho Brahe. Out of astronomy, most people have not heard of Tycho Brahe. Right? And this is true in artificial intelligence, and I feel it's very, very true. The majority of the grunt work is in gathering data, cleaning data, preparing data that often occupies 90% of your time. That is the hidden work that people don't see. What we see in research papers, what we see everywhere talked about, is finally the last 10% of the work, the AI algorithms and so forth. You guys are learning the AI algorithm, so it is all right. It's good to be excited about it. But don't forget the hard work that goes before you can feed your data into the AI algorithm. It's still a very laborious and manual task. Right? And it is as worthy of recognition as Tycho Brahe was, along with Kepler. Right? With those words, I'll end today's first quiz. Let's take a break for half an hour and we'll regroup, guys.
Asif, since you finished, I was about to say something else because the discussion about transcendental equations came up. And it's very interesting learning that nature represents itself as a transcendental equation. Is it just because of those transcendentals couldn't be expressed in could not be modeled by these AI models that, we take that as the physical representation, and then when we know, like for example, the Weibull equation or something, it's coming from the least, the weakest link failure model. So we take that as the basis, and then we apply on top of it, collect the data, fit to the Weibull equation. That is the data science part.
And
but the transcendental.
That is data science. You do fit that. In fact, reliability engineering, machine learning aspect is fitting it to these models, Weibull, Gompertz, and so forth.
Got it. So the Weibull is something that AI model would not have given, right? So we,
no,
do you mean that?
See, the thing is, you take a sufficiently complex neural network, it will internally model it as Weibull. It will learn the Weibull, but it won't be able to tell you that. Because the way it has learned is so very complex, it won't spit out the Weibull equation for you. In other words, it doesn't produce a closed form analytical equation. It just does what Weibull will do. It will make predictions accurately.
Oh, so you won't know the physical reason why it aren't.
Yes, you won't know. That is the problem. And that is the problem with AI at this moment, which is why if we could have it explain to us what it did, it will actually help us further science. Yeah?
All
And we'll
right.
talk
I
about
think there's a whole book by Weibull. Actually, I was reading that because I'm from the reliability engineering field, and it's a Bible for us.
Oh,
And it's
excellent. Sorry, I can't from the screen see who you are. Could you name yourself?
Balaji.
Oh, Balaji.
This is
Excellent.
Balaji.
Balaji, you have never come to my office, have you, at Support Vectors?
Yes, I have come once when I started. So
Oh,
that's
you
the
did?
only one side.
You probably haven't seen. I have a shelf full of Weibull and Gompertz.
I think the shelf behind you showed me, or on the right, I don't know. One of the place I saw that book. You showed me, yes.
Yes, I'm very, very fond of Weibull. It has a lot of applicability in survival analysis, cancer, and so forth, and many places. You call those models accelerated failure time models. You're probably aware of that.
Yes.
Yes, excellent.
Very interesting. Thanks for the explanations today.
Yes, you're welcome. See, I'll just, since you asked this question, see, one of the most amazing things, and Einstein used to say this, that the most incomprehensible thing in the universe is that we can actually comprehend it. We can actually understand it with mathematics, right? With all these transcendental functions and so forth. Now, why in the world can we describe the universe so accurately, with such uncanny accuracy, with simple transcendental functions? All of these equations and laws of physics, and they are very simple, and yet they can describe the universe. It's the most amazing thing. And the same applies to AI. When you come here, you'll see that the AI architecture, the kind of mathematics that goes into it is very trivial. Some amount of linear algebra, a little bit of probability theory, right? And that's about it, right? Some vector calculus, some basic calculus, linear algebra, and probability theory. That's all that goes into it. And yet it is able to do such wonderful things, That's what we looked at. It can translate languages. It can, recognize pictures. It can do all sorts of amazing things today. So that's the amazing thing with science and knowledge. All right, guys, I'll stop this session. I'll stop the recording and stop live streaming.